Hey folks, this is our first example of determining the electric field, the function of the electric field created by a charge. And our first charge distribution, I'll actually label it number one here, is a line of charge. And we are going to put ourselves off one end of the line of charge. I did write down the equation that we talked about in the previous video, so it's right there, but if you don't need to recopy that if you don't want to. Let's put some numbers here. Let's say that let's put some variables here. So let's call this D. That's actually a constant. That's how far away you are from the end of the bar. And then we'll make the length of the bar L. And we'll assume that it's fully charged with some charge Q. Okay. And we know that since it's a line of charge, it has a line charge density of Q over L, which is equal to dQ over dL. Okay. Now, we're going to try to use this equation up here. Okay, so we have to figure out how to write dq. Well, you kind of have most of the work done for you right there. You're going to get dq by itself. dq is equal to q over L, those are constants, times dL. All right. Now, we still have a couple issues here. First of all, the r hat. Okay, so let's say you look at some small chunk of the bar. So there is our dq, and let's say it has a length dl. Okay, that's what these are in this equation right here. Well, I think you would agree, assuming the bar is positively charged, and for all these examples, we're going to assume positive charge. If something were negatively charged, we get the same function, we just point the exact opposite way. So for a positive charge, I hope that you would agree that every little positive charge would make an electric field outward, which at our location is left. And so no matter which dq I pick, they're all going to make electric fields pointing to the left. So in this case, this is one of the few cases that we're going to have, you don't actually have to vectorially add. You're just simply adding because all the vectors point in the exact same direction. So for this one and this one only, we're going to ignore r hat. Okay. Now, if you rewrite the equation, sorry about that. If you rewrite this equation, okay, without the r hat in it, you get E equals K, the integral. So dq is Q over L dL over r squared. So we are part the way there. Now, people are anxious to integrate, but we're not ready to integrate yet. Okay. So here's a couple issues. The first issue is we still have two variables. They are not the same. So we have to, in order to integrate, we have to get this down to one variable to integrate. Secondly, we have to worry about our limits. Okay. So what does radius vary from? In other words, where does a charge exist relative to our point? So we are standing here. The charge starts how far away from us, and the charge ends how far away from us. In other words, what's the starting radius and what's the final radius? Well, the starting radius is d. The final radius is d plus L. So that's your limits. That's where the charge exists. Now, how about getting dl and r into one variable? Well, it turns out that that is pretty easy. So if we look at, let's say, this little chunk right here, and just for our view, I'm going to extend it up just so we can see, okay? Well, what's dl? Well, dl is simply the width of that little chunk, okay? Well, what is r? Well, there's a beginning radius that goes to there, and there's an ending radius that goes to there, okay? Well, if I subtract those two radii, that's dr. Well, if you look at that picture real carefully, if I subtract these two radii, I get a dr, and the width of this little chunk is dl. So it turns out in this case, dl equals dr. So we're going to sub in for dl, we're going to put a dr there. So we're going to integrate k. Now the other thing too, I'm going to go ahead and take the q and l out of here because they're constants and I don't need to integrate them. We're integrating from d to d plus L, dr over r squared. And that's the same thing as integrating r to the -2. And if you use your power rule for integration, you add 1 to the exponent, so you get r to the -1, and you divide by that new exponent, which is -1. So you get r to the -1 divided by -1, which is negative r to the -1, or better known as -1 over r. And so you would rewrite this as kq over L times -1 over r, and you have to evaluate that with your limits, d to d plus L. Okay, and if you do that, now we're just doing a little substituting in there. You would get -1 over d plus L minus 1 over, or no, minus negative, sorry, 1 over d. Okay, which if you tie this up a little bit, so this is our electric field, you get kq over L times 1 over d minus 1 over d plus L. Okay, so that is our electric field. You can also write this in terms of lambda. Q over L is lambda, so you could write this way. It kind of depends what they give you in the problem. So you can write it this way, and it's the same exact thing. All right, I'm back. Sorry about that. So you can write this electric field in either of these versions is fine. Now, I have two important things to kind of mention about the result, or actually three. First of all, don't memorize the result. I'd never memorize these things. You need to know the process. That's the more important thing. Number two, the whole limits thing. Let's say this problem were on a number line. So let me recreate that picture really quick. And so let's say here it is, and let's say here's our spot. Let's say this were a number line such that this was at x equals 2, this was at x equals 5, and this was at x equals 9, okay? And you were integrating, okay? So you're integrating, and we ended up integrating. We had kq over L outside of this, right? So kq over L, and on the inside of this, we had dr over r squared. Okay, so if you were doing that, what does your radius start at and end at? So where does the charge start relative to us? So it starts 3 away. We're at 2 and the charge starts at 5. That's 3 away. And then what's the final radius? How far is the final charge from us? Well, that's 7. It's 9 minus 2. So this is one way to get that answer. But what if you see a test, or they ask you a question in terms of x? So like this is, these are values of x along the x-axis, 2, 5, and 9 there. How would you write this in terms of x? So you got kq over L, the integral. Okay, so what if they wanted dx instead of dr? Well, then you wouldn't have r squared. You'd have something involving x squared. What does x actually vary from? Well, it varies from 5 to 9. That's what the two values of x are at the beginning and end of the bar. Well, how do you adjust this equation so that it will give you, these should end up with the same answer if I actually evaluate them. You should get the same answer whether you do it in terms of r or in terms of x. Well, if you make this x minus x naught being 2, you're going to get the same answers, because think about it. If you plug in 5 into there, 5 minus 2 is 3. That's our first limit. And if you plug in 9 into here, you get 9 minus 2, which is 7. That's your other limit. So you might see that. You might see it written in terms of r, or you might see it written in terms of x. So just be able to convert from one to the other. Okay. The other thing I want to mention to you guys, let's look at this final answer very, very carefully. Okay, and actually I'm going to use this version up here. Okay, so let me rewrite that. Okay, so E equals KQ over L times 1 minus D minus 1 over D plus L. Okay, well, let's say you were looking at that meter stick. There it is. And let's say you walk really far away from it. Like really far away, like 1,000 meters away. Well, if you walk really far away from the meter stick, again, this would be D, and this, the width or the length of the meter stick would be L. What we're talking about is we're saying, what if D is much, much bigger than L? What does our electric field look like then? Okay, so let's try that out. Let's take this equation and imagine that D is much, much bigger than L and see what we get. So we're going to do a little bit of math here. So we're going to have KQ over L. For the fractions here, I'm going to get common denominators. The common denominator is D times D plus L. So the first term becomes D plus L over D times D plus L, and minus the second term becomes D over D times D plus L. And if you subtract those, the D here and here subtract and get 0, you still have an L there though. So you get the following. You get E equals KQ over L times, let's see, L over D times D plus L. And something else happens. This L drops out, right? Okay. And you're left with the following. KQ over D times D plus L. Now, this is the next thing I'm going to show you is something that we use a lot in math and physics. And we say, okay, limits as something approaches something. So as D becomes much, much larger than L, if you look at addition and you're adding D plus L, well, that's roughly equal to D if D is much, much bigger than L. So for instance, if D is 1,000,000 and L is 2, who cares about the 2? That's about 1,000,000. So this is roughly equal to KQ over D squared. Well, what does that look like? Well, that looks like the electric field created by a point charge. In other words, when you get far, far away from the meter stick, hey, it looks like a point charge to us, and it behaves like a point charge to us. So you're going to notice that in a lot of the examples we do is when you get far away from them, they should look like a point charge, and the equation should reduce down to KQ over R squared, basically. All right, I'll see you on the next example.